everyone. Welcome back. This is section 3.2, what we're going to be doing in this section. So last the chapter 3.1, section 3.1, we talked about mean, the median, the mode, and how is it resistant versus not resistant. We talked about that the median is resistant where the mean is not resistant. Now in 3.2, we're going to be looking at measures of variation. And what measures of variation is about, let's talk about the definitions. Variation is the single most important topic in statistics. So this most important section is in this book. So in this variation, we talk about something called the range, the standard deviation, and variance. We're going to be looking at all those three characteristics throughout December. Because this involves statistics or numbers, our focus is not just on computing those numbers, but actually understanding and developing the ability to interpret and understand what they actually mean. So we're going to talk about range, standard deviation, and variance. What is the round-off rule? So in the mean and the median and the mode, or the mean and the median, it was one round-off rule. The round-off rule for this is when rounding the value of measures of variation, we actually are going to be carrying out one more decimal than the original data. So if the original data, let's say it's a whole number, we're going to round one decimal. If the original data, so this is the original, and this is a round-off rule. If the original data is has one decimal place, well, then we're going to round to 2 decimal places. So you add one more to whatever you're given. Okay, so you're going to carry one more decimal than the original set of the data. What is the range? So the range is pretty much your maximum value minus your minimum value. Let's say you're given a set of data. So you're just going to grab the largest data value and subtract it to the minimum data. So then that way you're going to look at the range of the data. So how does your data kind of fluctuate? Questions so far? They're fine? Everybody can hear me well? So on this one, we're going to talk about what is the important property of range. So the range is not resistant. Again, what if we have an extreme value like the max or min? This is a lot like your mid-range. Remember, the mid-range was the highest plus the lowest divided by 2. That was non-resistant. So our range is also non-resistant because of that same property. Okay? Because an extreme value can make your range change. Because the range does not usually have a maximum and a minimum value, it does not take every value into consideration, and therefore it doesn't truly reflect the variation among all of its data values. So when we look at the range, we only look at 2 pieces of information in the value. We don't have enough information to kind of truly reflect what's going on in the problem. I think that's what this is saying. Let's look at the example. Let's look at this. This is the example that we saw previously. So how would we see the range? Well, the range is the highest minus the lowest. So it would just be 75 minus 20. That gives us 55. So 55 is the range. 55 minutes would be the range of the problem. That's how you find the range. The maximum minus the minimum. Now, the standard deviation is different. You can calculate the standard deviation by hand, which takes a little bit more process. So the standard deviation is the set of sample values denoted by S, is a measure of how much data values deviate away from the mean. So it's actually the distance away from the mean. So we have S, the notation of S is a sample. So we have 2 types. Remember, there's a sample standard deviation and a population standard. If it's a sample, it looks like a little S. It's just an S. If it's a population standard deviation, then we have sigma. This is called sigma. So sigma is the population standard deviation. So again, we're able to calculate, if we go back to our calculator If we go, let me share my calculator. Let me see if I have it open. See how we have calculate? Again, we said we're gonna hit on stat and then we put edit. Notice how we listed our values already. These are the same values that we had, I believe. I think this is one more. Yeah, it should be 11 data values. So then with those data values, we select stat, and then we did count, and then one bar stuff. And then if we scroll down and we click on enter, it's going to give us this value. Do you see that this SX? This is the, if I'm zooming in, let me see if I can zoom in. Control plus. I don't think it's letting me. But do you guys see this little S of X? It says 16.55. That is the sample standard deviation. And then there's sigma of X, that would be the population standard, 15.78. And this was our mean. This is our sample standard deviation, and then we have our population. So just by basically putting it on your calculator, you're able to find the standard deviation. You can also do this using Wolfram Alpha online. There's tons of calculators where you can find the standard deviation. This is the actual formula. I'm not going to ask you to ever use the formula of solving standard deviation. So this is the summation between each of the values minus the mean of this value. So this is the sample mean squared divided by n minus 1. So n is 11. In our texture of the problem, minus 1 would be 10. So again, for us, when we found this on our calculator, S of X was about 16 point, go back, 60. It was 15 point, oh no, sorry, our sample was 16.555. So our original data it has a whole number, right? As our value. So then our round off rule would be 1 decimal. So 16.6 would be our sample standard deviation. Any questions on calculating standard deviation? Again, there is. If I'm going to put it on the chat, so then you can use the 84 calculate that feature, or calculate 84. Let me put that on the chat. So if you want to play with that, it's for free. This is from the App Store. But there's also the website Wolfram Alpha that you can just literally put in the points or the numbers on your data and put standard deviation of, and then just put the data and then enter, and it's going to give it to you. So you can do that. Again, I'm not going to ask you to do the final. So I gave those to you on the chat. So what are the important properties of standard deviation? The standard deviation is a measure of how much data values deviate away from the mean. So we know that the mean was roughly 39. The standard deviation will never be negative because it represents the distance away from the mean. Okay. Larger value of S indicates there's more variance. Okay? That is the meaning of the interpretation of standard deviation. And then let's go over the important properties of standard deviations within that. We have the standard deviation S can increase dramatically with one or more outliers. So what do we know? If it's going to change, then this is non-resistant. Standard deviation is not resistant. So then this is not resistant. Because then your numbers can change dramatically with one or two outliers. So the units of the standard deviation S, such as minutes, feet, and pounds, are the same units of the original value. So nothing is going to change. Your units are going to stay the same. The the sample standard deviation S is called it's called a bias estimator because it's biased responding to the population. So the sample standard deviation S is a bias estimator of the population standard deviation sigma, which means that the values of the sample standard deviation do not center around the values of sigma. Right? So it's a bias estimator. So depending on the sample size, that's what you're going to get as your sample standard. That will not necessarily reflect your population standard deviation. So it's biased around the sample. That's what this is saying. A bias estimator is biased around the sample value, not to the whole population. That's why a population standard deviation is different from a sample standard deviation. Just making sure that you understand and how to separate those will make sense. Do you have any questions about that? What does it mean to be a bias estimator? Anything of that nature? So far, so good, everyone. Okay. So I'm looking at the chat. So let me know if you have any questions, and if you're planning on downloading Calculate 84, that's a wonderful tool to have. And then you can use it when you're doing your homework, and then your quizzes, because it's gonna come up again. We're gonna use this a lot. So the way to calculate standard deviation, we already did this using our calculator. If you would have to find it by hand, you would first have to find the mean, which we already did using our calculator, and then you would have to take the mean and subtract it to each of the values and then square each value. So look at this. So first you do x minus xr. So I'm going to take, so these values, 10.9 is the subtraction between 50 minus 39.1, 25 and 39.1, 75 and 39.1. So we're not going to be asked to find that. And then you have to square those values. So that's the square of 10.9. This is the square of 14.1, and then the square, and then you're going to have to add all these. You will not need to do this by hand. So there is our solution that we got from our Calc 84. This was x of x. When we rounded, right? So 16.55, and we said we round off one, the round off row was 1. So making sure you know how to find the standard deviation using your calculator, that would save you hundreds of times. Any questions on standard deviation and how to calculate it? Questions on the chat, anyone? So far, so good? Yeah. So there it is. We found a 16.6. Again, the rule of thumb. Now, we have another rule of thumb. This is the range rule of thumb for understanding standard deviation. So the range rule of thumb is the simple tool for understanding and interpreting standard deviation. The vast majority, or 95% of the sample values lie within 2 standard deviations away from the mean. So to understand that, we do our and I'm terrible at graphing again. So here, so look, this is our mean. This is 1 standard deviation away from the mean. This is 2 standard deviations away from the mean. So what this is saying is that 95% of the whole tally, so the shaded region, so this is 1 standard deviation, negative and negative 2 standard deviations away. So this area, this yellow region makes up 95% of your data. 95% of those samples lie within 2 standard deviations away from the mean. That's this interpretation. So then the range rule of thumb for identifying significant values is you're going to be significantly low if your values are mu, the population mean, minus 2 standard deviations away. You are significantly high if your values are the population mean plus, right now these don't have meaning to you because we don't know how to find M and sigma yet. We will. So significant values is if you're in the outliers, are you significantly low? Are you significantly high? Or you do not have a significant? So you're closer to your mean. So these are further away. These are further away than the mean. And they have meaning because they have more variation. We talked about that. The more standard deviation it has, the more variation. So further away from the mean. That's what this means. Cool. Any questions on this one? I know that this seems off a little bit just because of the fact that these symbols don't really mean anything to you now, but they will. There is another rule of thumb, the rule of thumb for estimating. I would focus more on this graph. That can give you an interpretation. About 95% of the sample region is within 2 standard deviations away from the mean. We're gonna look at that. We also have a range rule of thumb for estimating a value of standard deviation S. So to roughly estimate a standard deviation from a collection of known sample data, we can also use this. This is more estimation. This is a rough estimating, which is your range, which is your max value minus the min value divided by 4. And this would just be an approximation. This would be a rough approximation. Okay, this is the very estimated. The more exact is the one that we did using our calculator and the formula with free math. Standard deviation of a population. So this one, again, we're not going to be asked to calculate it by hand. This one, we're going to grab it from again, a calculator that we had. If we go back to our calculator, it's this sigma of x. You guys see it? So in this case, sigma of x was 15.7852. So if we round that, that's 13.8. So do you see the S of x and then the sigma of x? The sigma of x is the population for this particular individual. So let me go back. So when we saw the sigma of x, we saw that this was 15.785T. We round that off by 1 decimal. There's also called, so that is called the population's standard deviation or sigma. There's sigma squared or S squared is actually, all you do is you square the standard deviation. The variance, the sample, there's 2 things. So the variance of a sample and the variance of a population. The variance of a sample is S squared. All you have to do is take the square of your standard deviation. That will give you the variance. That will give you the sample variance. When you take the square of sigma, if you take the square of the population standard deviation, you're going to get the population variance. So variance and standard deviation go hand by hand. So if you have one, then you have the other because you either square it or you find the square root of it, one or the other. So let's write that down. Standard deviation and variance go hand in hand. They go together. What do you mean they go together? Yeah. So remember, S, the standard deviation, is the square root of your variance. This is for the sample. Or I can square it, or S squared is equal to my standard deviation square. And then whereas if you have the sigma, a square root of sigma squared, if you take the square root, for the square root of the variance gives you, in this case, gives you the standard deviation. That's important. So they go together. So this is the notation you have to understand. This is the notation summary. S is the sample standard deviation. S squared is the sample variance. Sigma is the population standard deviation. Sigma squared is the population variance. Any questions so far? So what is the important property? So on the one before, standard deviation had its own important properties of variance. The important properties about the variance is the units of the variance are the squares of the units of the original data value. The value of variance can increase dramatically with inclusions of outliers. So again, the variance is also non-realistic. The value of the variance again is never zero or it's never negative. S squared is again, so look at the difference. The sample variance is unbiased estimating. So standard deviation biased, S squared is unbiased because it's squaring. Okay? So F, the difference between the variance and the standard deviation is that the standard deviation is biased. It's called the bias estimator, where variance is an unbiased. You don't have to worry about why they divide by n-1. We don't use the formula, but just to explain why is that the n-1 can be assigned without constraints. Given a mean, we can use any numbers between n-1. But the last value will be the automatically determined. So when you do an n-1, you do something called an underestimation. So we want to always making sure that we take care of it. So if we remember for standard deviation, I'm gonna make this a black. If you recall, in standard deviation, the formula was the square root of x minus x bar minus x squared over n. Whereas this was for the sample, and for the population, the only thing that changed is this n was n-1. And that was because we have to look at what happens when we overestimate or underestimate. So we have to take into consideration how many n values do we have. We actually don't know. Remember, for a population, it's more difficult to have something that is actually predetermined. We don't know. So then we have to use this n-1 criterion. Questions so far? I had to connect my computer. Any questions? Can you guys all hear me well? Do you guys hear background noises? We're good? Okay. Let me know. So we're almost done with this is 3.2, and we have one more to go, and then that's going to be the end of the lesson. We do have 30 minutes. This is one of the most important rules in statistics. So the empirical rule tells you about how much percent you have within a standard deviation. So about 68% of all of the values will lie within one standard deviation away from the mean. About 95, that's what we saw earlier with the yellow when we colored in our normal curve and we saw 2 standard deviations away was 95% of all data. So about 95% of all values fall within 2 standard deviations away from the mean. And about 99.7 of all values fall within 3 standard deviations away. So look at this. This is what I want to talk about. So remember, the empirical rule goes by a normal distribution. This is a normal distribution, guys, what we have. So see how this has a peak? The center is the sample mean. So when we are one standard deviation away, we're talking about this piece. So if we divide it by 2, because it's when you have a normal distribution, you have symmetry. It's symmetrical. So if you cut it in half, you have half of one side, half of the other. So one standard deviation away, you're cutting it in 2. So 68 divided by 2, we get this 13.13. We cut it in half, the 68%. And then 2 standard deviations away, it's just a green one. So 95% lie within this data. So it's more shaded region. And then the last one, the orange, will be 3 standard deviations in. So I'm going to color it in. Except this piece. So we're not shading here or here like the outlier. So you're not shading this part. So everything will lie within 3 standard deviations away. And that's when we're going to study z-scores and positive and negative z-scores and what does that mean for us. So our normal distribution makes 100%. So if I would completely fill out this, that would be 100% of the data. But the further I can get is 3 standard deviations away, which is 99.7, but that's really, really close. So if we look at this one, if we look at an example, it says IQ scores have a bell-shaped distribution, so they're already telling us it's normal, with a mean of 100. So I'm going to do here, I'm going to do 100. That's my mean. My mean is 100. And it's telling me that the standard deviation of 15. So the standard deviation is 15, and I have the value 70 and 130. How many standard deviations away does that? What is that? So look, we look at the distance. So the distance is 30. So 30 is equal to 15 times something. So we know that the standard deviation is 15. What is this? 15 times what? Give me 30. Put your answers on the shot. What am I missing there? What do we have? 15 times what gives me 30? Where am I getting the 30 from? The area between a 70 and 130. Are we here? So what is it? 15 times what gives me 30? Are we on here on the chat? There it is. So we get 2, right? So 15 times 2 will give me 30. So this means that I'm 2 standard deviations away from the mean. Okay, we recognize that 70 and 130 are exactly 2 standard deviations away from the mean. So if I'm 2 standard deviations away, that means about 95% of all IQ scores are between 70 and 130. That's what the interpretation of this example is. This is called the empirical rule. We also have another theorem, which is called Chebyshev's theorem. Chebyshev's is something further away than the empirical rule. That also stands for percentages. So what happens when the k standard deviations away are 2 and 3? Okay, so that means I'm going to use this formula, which means 1 minus 1 over k squared. When I plug that in, if I'm using Chebyshev's, I do 1 minus 1 over 2 squared, 1 minus 1/4. But what's 1 minus 1/4? Do we know how to do fractions here in this class? So 1 is the same as 4 over 4 minus 1 over 4. That's 3/4. As a percent, that's 75%. So that's how we got this value. So at least 75% of all these values lie within 2 standard deviations away from the mean for proportions. Okay, it's not the same as when we have a uniform distribution when we're using that curvature. It's not the empirical rule, okay? This is different. When k is 3, well, now we do 1 minus 1 over 3 squared. 1 minus 1 over 9. So 8 over 8 minus 1 over, sorry, this should be 9 over 9. The denominator, 9 minus 9. Over 1 minus 9, we get 8 over 9. So 8 over 9 is 89% of all values will lie within 3 standard deviations away from the mean. Now, this was a different one because the first one was using the empirical rule. Now they're asking us for the Chebyshevs. IQ score have mean, so we already know that the mean is of 100 and standard deviations of 15. What can we conclude about Chebyshevs? So since we know that the standard deviation is 15, and we're looking at the Chebyshevs, we want to know that because we know that this is 2 standard deviations, right? So again, when we had the 70 and the 130, the distance is 2 standard away. So then your K will be 2. This 2 standard deviations away is now K being 2. So you do 1 minus 1 squared. So we did 1 minus 1 fourth. We did this already, 3/4 or 75%. That means that at least 3/4 or 75% of the IQ scores will lie 2 standard deviations away. And look at the values. That's 170 and 130. If I want 3 standard deviations away, what would that be? So 3 times sigma, it's 3 times 15, that's 45. So you're going to do 100 plus 45 and 100 minus 45. That's how we get the 55 and the 145. And that's 89% of the values will lie between 55 and 145 IQ squared. So that is Chebyshev. So we talked about empirical rule and we talked about Chebyshev. So the standard deviations away will give you K. The last few slides talks about the coefficient of variance, coefficient of variation. And to do that is actually very simple. There is a sample coefficient of variation and a population coefficient of variation. For a sample, you have the sample is the standard deviation divided by the mean. So let's write them down. So this is the standard deviation. The sample standard divided by the sample mean times 100. Where here is your population standard divided by the population mean times 100. Okay, so we're going to use the Randolph rule. It's 1 decimal point. So that is going to be consistent. And it's going to be a percent. Coefficient of variation is a percentage. That's why we multiply by 100. So let's write that down. Let's write this down. So these are some formulas. And we'll just finish off these slides with just finishing with the example of a biased and unbiased. And we've talked about this. A sample standard deviation acts as a bias estimator where a sample variance is unbiased. So a bias estimator is that it depends on the sample. So a bias estimator of a population standard deviation, which means that values of standard deviation do not tend centered around the population standard deviation sigma. Whereas your variance, it is. So your S squared, your sample variance, is an unbiased estimator of the population variance, which means that the values of your sample variance will center to your population variance. So instead of systematically tending to underestimate or to over and underestimate. So what are we getting out of this? That the sample standard deviation is biased. So it's not a really good estimator because it's biased. Whereas variance is an unbiased estimator, which allow us to have more accurate results. So bias versus unbiased. And that is the end of section 3.2. Okay, so we do have 20 more minutes, and let's continue to section 3.3, and that is going to be the end of our lecture today. And this one, I'm not sure if we're going to be able to finish because it's 38 slides. So let's attempt in completing what we can. So this concept, so what does this mean? Section 3.3 measures of relative standing and box plot. This section introduces measures of relative standing, which are numbers showing the location of data values relative to one another. The most important section is the z-score. We can discuss percentiles and quartiles, which are common in statistics, as another statistical graph. So we can find the percentiles and quartiles using our calculator, and we calculate 84. And then we're going to be doing box plots. And then there's a way to find z-scores using your calculator, but I want to show you this by hand. So you can use your calculator to find a z-score, and you can also do it by hand. So that's what we're going to be learning today. So to find a z-score, you actually find the z-score by this formula, x minus x bar. So the value, the particular value minus the sample mean divided by the standard deviation, or the population z-score is when you have your value minus the population mean divided by the population standard deviation. Okay, so let's write those out. So again, we have a z-score when we have a sample, and it's different z-score when we have a population. So how do we use the round-off rule for z-scores? The way that we round z-scores is 2 decimal places. And that's going to stay the same, so 2 decimal places. What are the important properties of z-scores? A z-score is the number of standard deviations that are given on an x value above or below the mean. So every time we're going to have different z-score depending on the value that we're given. Z-scores are expressed as numbers with no units of measurement. A data value is significantly low if the z-score is less than -2, or high if it's more than 2. If an individual data value is less than the mean, its corresponding z-score is negative. You may have negative z-scores, and the way that we understand that is when we look at our distribution, normal distribution. Here is our mean, or x bar, and we have values to the left. So if our mean is 0, then these are negative z-scores. And these are positive z-scores. And the middle is 0. This one has a z-score of 0. So to the outsiders, to the right is positive, to the left is 1. So we're going to look at this example. We're going to calculate standard deviations next. Or sorry, z-scores next. Which of the following 2 data values is more extreme relative to the data set from which it came? So the 99 Fahrenheit temperature of an adult among 106 adults with sample mean. So they're already telling us what the sample mean is and the standard deviation. Okay. And then we have the 5.7 gram weight of a quarter among 40 quarters with the sample mean. This is now X bar grams. So we're looking at temperature and we're looking at grams. So we're going to calculate the z-scores from each. So the z-score for the first is x minus x bar over x. So what's x in this case? X is 99, what we're given, minus x bar, which is 98.2, all over 0.62. So we're going to use our calculator for that. And then we have, that's the first z-score. The other z-score is 5.7790 minus 5.639 all over our standard deviation, which is 0.06194. So we're going to be calculating this using our calculator, of course. So let's plug that in. So let's go back to our calculator. So over here, I'm going to say, okay, I'm going to do 99 minus 98.2. I'm going to use that number and I'm going to take that number, the answer, and I'm going to divide it by 0.62. And that's going to give me a z-score of 1.29. That's my first z-score. The next z-score is 5.7790 minus 5.6390. That's the top, divided by 0.06 to 0.06194. Let's check if that's right. And that's 2.260. Which one is greater than 2? The second z-score. So that's more significant. Because what did we say at the beginning of z-score? If the z-score is greater than 2, so if we go back, if the z-score is greater than 2, this is significantly high. For the second example, we have a significantly high z-score value. So we found the two answers, 1.29 and 2.26. The interpretation of it is that the z-score of the 99% is 1.29 standard deviations away from the mean, above the mean. And the weight of a quarter is 2.26 standard deviations. So that means that the weight and the temperature is more extreme than the body temperature. So the weight is significantly higher because it's greater than 2. Okay, so the 2 is a rule of thumb. Yes. Again, when you're significantly low, your z-score is below -2. If it's greater than 2, that means, so if my values are -3, -4, significantly low, significantly high is on the other range, which is 2 or higher. And when you're not significant is when your z-score is between -2 and 2. So that is a rule of thumb. Let's look at this one. Among the earthquakes listed in the data sets of 24, one of the stronger earthquakes has a magnitude. So this one's already telling us the magnitude of 4.01. The magnitude are measured on Richter scale and only earthquakes of magnitude 1 or higher. So let's write that down. 1 or higher. The magnitudes of 1 greater than 1 are included. The 600 magnitudes in the data have a mean, so the mean is 2.572, and a standard deviation S of 0.651. So what do we have to do? They're already telling us the magnitude of 4.01, and then the mean. So we have x minus x bar over x. So if we're looking at a magnitude, we have x bar to be 4.01 minus the mu, the x bar. This is the mean. So we're finding the z-score right now, 2.572 divided by 0.651. Let's go ahead and find that using our calculator again. So let's go ahead and go to our calculate 84. And I'm going to punch 4.01, which is the mean that's given, the original, minus 2.5. That's the sample mean, 2.572. Let's find that first. And then we're gonna take that number and we're gonna divide it by 0.651, which is 2.20, which is greater than 2. So this is significantly high. Okay. Why is this significantly high? Because it's greater than 2. So let's go back to our notes right here. So 2.21, because the magnitude converts to a z-score of 2.21, which is greater than 2, the magnitude is significantly high, which we knew that. So that was in terms of z-scores. What about percentiles? So percentiles are dividing. So for example, if we're giving our data, we partition this in data sets of 100, where each of them are 1%. So there's a formula for finding percentiles. So the percentile is the number of values less than X divided by the total number of values times 100. So it's a percentage. That's going to be the percentage of the value X. So the number of values less than X divided by the total number times 100. And we're going to do an example. So we have this down. This is the table that we have. Notice that this is in order from the smallest to the greatest. And it's saying the table is 50. So N, we know N, the total is 50 of them. The waiting times, the times are arranged in order. We want to find the percentile wait of time of 45 minutes. So if we're looking at the percentage, find the percentile for waiting time of 45, this is 45. So if we go over here, it's saying the percentile of the value is the number of values less than X. So less than that is all the ones on top. So 1, 2, 3, that's 30. 1, 2, 3, 4. This is 1, 2, 3, 4, 5, 6. So then the ones before this, so all of the values are 36. So 36 over 50 times 100. That's how we're going to be finding the percentile. Where did I get the 36 from? The values were less than 45. So all of these pathways. So if I calculate this, so if I do, what's 36 divided by 50? That's 72 or 0.72 times 100. It's 72%. So it's in the 72nd percentile. And it looks like this. So the percentile of 45 is 72. Thank you, Joe. Exactly. So then we have 36 divided by 50 times 100, 72 percentile. So then that means that the wait time separates the lowest 72 from the highest 28. Where did they get the 28 from? Well, 100 minus 72, the remaining are 28. So the lowest is 72%, lower than 45, and more than 45 minutes is 28%. So roughly, to get in line and get into the ride, is roughly going to take about 72% of the people will do around 45 minutes for a ride. And let's look at the notation for percentile. N is the number of total values in the set. So we had 50 in this case. K is a percentile. So we have P to the 72. This little 2 is the percentile. That's represented by K. L is the locator. It's the position. So the position of this one, we didn't count it. But the position would be, we would have to count the position that it was in. So L12 would be the 12th position. P to the 25 is the 25th percentile, or it's also called quartile 1. Percentiles and quartiles go hand in hand. So this is how would we calculate it. We would start by sorting the data. We would find L is a locator. So the locator has a formula, which is K, the percentile, divided by 100 times N. K is the percentile, and N is the number of total data values. Okay. We would have to find, if L is a home number, then we're going to find what's going to be the middle. So if L is a whole number, the value of the closed percentile is midway between the L values. If it's not, then you just move it to the next one. So let's say if my locator was 12.3, I'll just go to the 13th slot. So what I'm gonna do is I'm gonna go back to my point, and if it was, let's say L was 12.13, I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then the 13th would be 25. If it would be 13, I would have to look at the 13 and the 14 and then take the median, add and divide by 2. If it would be a whole number, that's what this is for. To find P25, we're looking at the 25th percentile. We want to find the value, so we want the location. P25, we have K over 100 divided by times N. So K, we're finding the location. L, so K is 25 over 100 times, and let's look at our formula. Yes, we have K divided by 100 times N, and N is 50. So here we have, we're going to simplify this. So 50 and 100 will be 25 over 2. This is 12.5, which is going to go to 13. So we found that that was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 25. So 25 would be the location. For when we look at it, there it is. K divided by 100 times N, 12.5. So we just move to the, because L is 12.5, we go to the 13. For us, that was 25. 1, 2, we're just counting up to the 13. The last part is quartile. So again, quartiles is quartile 1, quartile 2, and quartile 3. So quartile 1 belongs to P25, the 25th percentile. Q2 is actually your median of the data, which is the same as your 50th percentile. And then Q3 is P of 75. Because we did percentiles, you should be good finding 75th, the 25, the 50, and the 75th quartile. So I would recommend doing this just because we have 2 more minutes and I don't want to rush. Because we did percentiles, you should be able to do quartile. Okay, so there it is. Quartile 1, quartile 2, quartile 3. And the last part is just some formulas. Q3 minus Q1, Q3 minus Q1 over 2. And then the last part is looking at, let me just scroll down, and creating this box plot. The box plot starts with the minimum value, quartile 1, quartile 2. So this would be P25, P50, P75, and then the maximum. And that's it. That is the end of the section for you. The last part is the skewedness. We talked about skewed. When the data is more to the left, when it's a normal, it's in the center. Uniform, where everything is kind of centered in the middle, everybody's the same. And that's it, pretty much. In this section was finding quartiles and creating a box plot. So they found for this, remember we did this was P25, then they found P50, and then they found P75. Okay. So I'm going to stop the lecture here, and class will resume next Tuesday. And then I will be sending you guys new lectures with a new notes. Remember that you have a discussion first. So let me start the recording.